Hi, and welcome to Week 7, Mini Lecture 3 of Thermodynamics for Educators. In this lecture, I'm just going to go over 3 quick examples applying some of the concepts that we learned in the previous lecture and giving you a couple of tips for homework problems to come. I'm going to start off with the following problem. Suppose you have an electric current flowing through a resistor. Say the current is 5 amps, the resistor is 120 ohms, and you allow the current to flow through that resistor for 10 seconds. Now suppose that the temperature of the resistor is held constant at room temperature, 300 Kelvin. We know that when current passes through a resistor, then the resistor heats up. If it's being held constant, that means that the heat must flow out of the resistor into its surroundings. Suppose we're asked to calculate the total change in entropy in this situation. Well, what is the change in entropy for the resistor itself? Well, the temperature is constant, the volume is constant of the resistor, we're not doing anything to the resistor. In fact, all of the other thermodynamic variables for the resistor are constant, so actually the entropy of the resistor itself doesn't change. Its temperature stays the same, therefore its internal energy stays the same, the total number of particles stays the same, and so on and so forth. So what is increasing entropy? Well, the surroundings must be. There is heat flowing into the surroundings. How much heat flows into the surroundings? Well, it's just equal to delta Q over T. Remember, the surroundings are held at constant temperature T, so we're using the formula for an isothermal process. The total heat that flows into the surroundings you can get from the standard formula for the heat dissipated by a resistor, which is equal to I squared R, where I is the current and R is the resistance, times the time for which the current is flowing. If you plug in the numbers, you'll get that delta Q is equal to 30,000 joules, and 30,000 divided by 300 gives you a total change in entropy in the surroundings of plus 100 joules per Kelvin. The total change in entropy to the universe from this process is the sum of the change in entropy to the surroundings plus the change in entropy in the resistor, which is plus 100 joules per Kelvin. Now, this is a vitally important thing to keep in mind. The second law of thermodynamics always refers to the change in entropy to the universe during a process, and that is the sum of the changes in entropy to all the components of that process. Often, the vast majority of cases when people think that the entropy during a process is decreasing occur because they are failing to take into account an increase in entropy somewhere in the universe. They've forgotten to take something into account where the entropy is increasing. If you get a total change in entropy that is negative, that means that you have forgotten to take into account the change in entropy somewhere. Okay, let's take another example. Let's suppose we take a block of lead that is at a temperature of 200 Kelvin and we dump it in a bath that is at a temperature of 100 Kelvin. Now, these are slightly funny temperatures. The bath must be filled with something like liquid xenon, for example, but let's put aside practical concerns for now. Now we're going to assume that the bath is large enough that its temperature doesn't change when you dump the lead block into it. We can make the bath as large as we like, or at least we can imagine it to be as large as we like. So that's what we're going to assume. Now the change in entropy to the block, the block's volume doesn't change, so we're dealing with an isovolumetric process, so we can use that formula. The change in entropy to the block is the heat capacity of lead at constant volume times the log of the final temperature of the block, which will be 100 Kelvin, divided by its initial temperature, which is 200 Kelvin. You can look up the heat capacity of a block of lead, and you'll find that the change in entropy of the block is minus 0.7 kilojoules per Kelvin. So the change in entropy to the bath occurs under conditions of constant temperature. So we use the constant temperature formula. Delta S is delta Q over T. Delta Q, the heat added to the bath, is just going to be CV delta T, equal to the heat lost from the lead block. So you plug in the numbers and you get that the change in entropy for the bath is plus 1 kilojoules per Kelvin. So the change in entropy for the universe, adding these two together, is plus 0.3 kilojoules per Kelvin. So again, the second law of thermodynamics is fulfilled, even though notice that it is allowed for, say, the entropy of the block itself to be negative, the entropy of the block to decrease. That has to be always compensated by an increase in the entropy elsewhere. Finally, one of the homework problems involves analyzing the entropy change when an ice cube melts and heats up to room temperature. So again, let me give you some pointers here. When an ice cube melts, it happens at constant temperature, 0 degrees Celsius or 273 degrees Kelvin. Therefore, the heat added to the ice from the room is equal to the mass of the cube times its latent heat. And therefore, the change in entropy of the ice cube whilst it's melting is equal to ml over T. Next, the ice water warms up to room temperature, In that case, the heat flow into the water is just equal to CV delta T. Again, it's a constant volume process. And the change in entropy for the water, again, we use the formula for the constant volume process. And finally, the heat lost from the room, delta Q room, is just equal to the heat added to the water whilst it warmed up to room temperature minus the heat added to the cube when it melted. Right, that's just conservation of energy. The total heat added to the water came from the room. Therefore, the magnitude of the heat added to the water is equal to the magnitude of the heat taken from the room. The room is always at room temperature, so the change in entropy for the room, we use the constant temperature formula, delta Q over T. The overall change in entropy for the whole process is then the sum of these three entropies.